Hey everybody, this is Mr. Walsh, and today we're going to be talking about electron configurations. And if you're following along, this is Unit 2, Section 5, but this is going to be Part 3. Okay, we did Part 2 in the previous videos, and so now we're going to look at Part 3. And hopefully this will kind of seal up some of the knowledge that we have, or make sure that we know what we're talking about. We talked about this. There are 3 vocabulary terms. You need to pause this. Okay, you need to know what the valence shell is. You need to know what valence electrons are, and you need to know what kernel electrons are. And we did this in terms of if we have a Bohr model of an atom. Okay. And the valence shell are the outermost. Okay, so we'll do something like this. So in this case, the valence shell is the outermost shell. Okay, in this case, the valence shell is 3. Let's see, 1, 2, 3. The number of valence electrons is how many electrons are in the valence shell, which in this case is also 3. And then the number of kernel electrons is the core electrons, the number of electrons that aren't in the valence. So in this case, it's 2, 4, 6, 8, 10. Okay. For carbon is here, so we're going to figure this out. It's going to be 1s2, 2s2, and then we make the big leap over here to 2p. 1, 2, that puts us in there. Okay. Sodium, 11 electrons. Okay. Sodium is here. So we're going to do 1s2. And then there's nothing else over here. So we come down here to 2s2. Remember, this is the S block. This is the P block. So 2s2. And then we make the big leap over here to 2p6. Nothing else over here, so now we come back down here to 3p, and then, or 3s, and then we go into 1. So 1s2, 2s2, 2p6, and then 3s1. Okay, and now chlorine, that one's over here. So we're going to start the same way. So with chlorine, we're going to start here at 1s2. We start all over again. We always start at the 1s. 2s2, 2p, right? 6, 3s2, 3p, 1, 2, 3, 4, 5 gets us to chlorine. Okay. Then you can try some yourself. Fluorine. Okay, you can pause it, get out a periodic table, do it up. Here's fluorine. So again, we're going to start at 1s2. And we come down to 2s2 in the S block. We make the big jump to here. This is 2p, 1, 2, 3, 4, 5, 2p5. Then magnesium. Okay, magnesium is here. 1s2, 2s2, 2p6, 3s, and then 1, 2 gets us to magnesium. Okay. So what we've been doing really is using the periodic table tell us what we got. All right, so remember that this is the S block, this is the P block, these are the Ds. We're not going to do too much with the Ds, but that doesn't mean we won't see Ds occasionally. And then here's the F block. Not only do we use the blocks, but we also use the periods, because we're going to go 1, we go 1s2, 2s2, 2, and it's almost like we should put the the periods over here, which represent kind of the energy level, right? 2p6, 3s2, 3p6. Like, we can keep going through all this, okay? So that's what we visualize when we're doing this on the periodic table that, looks like this, right? We have the F's, the P, the D's, the P's, the S's, right? And so you can kind of see that here we're going 1s, and then 2s, then 2p. And so the periodic table gets us to where we want to go, okay? So let's try some more practice. You can use the periodic table to do this. And again, you can pause to figure this out if you want, but let's do this in this order here, okay? So number 1, lithium. Lithium is here, so that's going to be 1s2, 2s1, because lithium is here. Calcium, I know I'm kind of going out of order, but I want to make sure I do all of these here. Calcium, which is down here, 1s2, 2s2, 1s2, 2s2, over here to 2p6, 3s2, 3p6, and then down here to 4s2, 4s2. Okay. We'll do boron and now titanium. Okay, so this is one of the only, titanium is a D block element here, so that's going to be a little weird. But let's do boron. Boron's here. Okay, so again, we're going to start 1s2, and then we're going to come down to 2s2. I don't know, my 1 is way far away, but that's okay. 2s2, and then back over to here, make the big jump over to the p's, to p1. Okay, now titanium is way down here, so start 1s2, 2s2, 2p6, and you can pause the video to see if you get your own answer here. 2p6, 3s2, 3p6, 4s2, and now here's the thing, the D's are shifted down by 1. So this is here the 3 D's. This is the 3 D's, not the 4 D's. If we take a look back at the hotel, okay, the point is, or the thing that we were looking at here is, remember that the 4 S's fill before the 3 D's because of this little space, even though they're on the 3rd energy level. So these are the 3 D's, and then below them, yttrium, zirconium, these are the 4 D's. Okay, so the D's are shifted down by 1. Okay, and so this then becomes the 3D12, becomes 3D2. Okay, and we can go up, we can do a couple more. Again, this is going to be a lot of practice here in this video. Okay, so chlorine. Okay, a lot of times good chemists will put Cl there so we don't confuse it, but chlorine is here, so we're going to go 1s2, 2s2, right? And then big jump over to here, 2p6, 1, 2, 3, 4, 5, 6, down here, 3s2, and then we're going to go 1, 2, 3, 4, 5, 5, 3p5. Then manganese is in the middle of the D block. So this is going to be similar to titanium that we did a little bit ago. So we're going to go 1s2, 2s2, 2p6, 3s2, 3p6. Okay, and that brings us here, and then 4s2. And then remember, these are the 3Ds. So 3D, let's see, 1, 2, 3, 4, 5, 3D5. Okay, so that's the electron configuration of those. So one of the things that we can do, though, is we can abbreviate by using the noble gases. The noble gases have the property of the physical property of having a full valence. Okay, so because they have a full valence, they have a chemical property of being completely unreactive. Okay? And so if they're completely unreactive because of their full valence, now we can use that to our advantage when doing electron configurations. Okay? And so what we would do is we would abbreviate by starting with the previous noble gas. Let's say we had this element here that we're trying to find. It doesn't matter which element that is, but what we're going to do is we're going to go backwards to xenon, and we would start with xenon, and that would represent 54 electrons. And all of those electrons were full up to xenon. There's no spaces, no anything to worry about. And then we can start down here with 6s, how many? 1, 2. 6s2. Okay? And what this does is this kind of highlights us being able to see how many, and this is my foreshadowing from the beginning that I accidentally put in. This gives us the kernel electrons, 54. This gives us the valence shell. And then this gives us the valence electrons. And it becomes easier to see when we use what we call the noble gas configuration. So we should practice this. Okay, so we're going to look at calcium. So what we're going to do is we're going to go to the previous noble gas by atomic number. So this is 20. Okay, so we're going to go backwards, 20, 19 to 18. So we're going to go to argon. Now that argon represents 18 electrons. And now we're going to go and we're going to pick it right up here. There's no other elements over here to worry about. So now we're going to come down and we're going to start with the 4s2. Okay? And so, again, the reason why this is great is because we know how many kernel electrons there are. There's 18 because argon is 18. We know that the valence shell right here is equal to 4, and we know that the valence electrons is equal to 2. Okay? This is a great way to show the valence electrons, the valence shell, the kernel electrons. Okay? It's one of the beauties of that. Okay? So now if we're given a noble gas to start with, okay, we can't just put argon in parentheses or in brackets. Okay? We still have to go to the previous noble gas. So we're going to go back all the way. Let's see. We started at 18, down to 11. And so we do neon. And then there's nothing over here. So now we have to come down to 3s2. And then we make the big leap over here to 3p6. 1, 2, 3, 4, 5, 6. And if you look, now if we look, let's do this. Kernel electrons here. This is 10 because that's how many electrons neon has. And then we have the valence shell, which is 3. And then here we have valence electrons, which is 8. And we know that the noble gases are characterized by having a full valence shell, 8 electrons. Okay. Okay, we'll go a little bit more quickly. Okay, so phosphorus, again, is here. So we're going to go back to the previous one, that's neon. Okay, so we go back to neon, and then we start at 3s2, 3p3. Okay, and we can go through the kernel electrons, valence shell, and valence electrons for all of them, but I'm not going to. Okay, chlorine is in the same period as phosphorus. Okay, so that's also going to be neon as the noble gas. And now we're going to pick it up with, let's see, we were at 10, so we have to go down here to 11, so that's 3s2, 3p5, right? Because we 3s2, 3p, 1, 2, 3, 4, 5, made the big leap. Okay, so now we're going to go down to francium and barium. It's going to be a little more challenging here to get this all on the thing here, but francium is way down here. So this is where noble gas notation comes into play for convenience rather than informational. Okay, nobody wants to go through the periodic table and be like 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d10, you know, blah, 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 all the way down to this, whatever this is, okay? So what we're going to do is we are going to, again, go backwards by atomic number. This is 87, so we're going to come back here to 86, which is radon, Rn. Okay? And then, I know it's really hard to get this into the, okay? And now, radon here. So now we're going to come down to 7s1. It's 1 in. Okay. Then we can do the same thing for barium. Okay. Same process. Barium, we go previous by noble gas. 56, 55, 54. So that's going to be xenon. And then we're going to come down and we go to 6s2. And that saves us from having to go through all of those crazy things, okay? And now we can still do the same thing. What's the kernel electrons? Xenon is 54 here. Okay, this is the valence shell. And then this is the valence electrons. We have 2 valence electrons, okay? So what we've done is we've basically gotten a ton of information from an electron configuration. Okay, we can look at this. This is an electron configuration, and we can say, what is the valence shell? Well, the valence shell is the biggest big number. So the valence shell is 3. How many valence electrons are there? 6. How many kernel electrons are there? Well, that's the stuff that's left over. Okay, what element is represented? Well, 2, 4, 10, 12, 16. So element number 16 on the periodic table is sulfur, or we could go through the electron configuration: 1s2, 2s2, 2p6, 3s2, and then 3p, 1, 2, 3, 4. Okay, so that's sulfur. What group or family is it in? Okay, well, this is group 16. It's in the oxygen family. Okay, doesn't have to be. We could also, instead of saying oxygen family, we could say the chalcogens. Okay, what period is it found? It's period 3. Okay, and then name an element that has similar chemical properties. Well, turns out sulfur, because remember the periodic table is organized by similar chemical properties, so sulfur has similar chemical properties to selenium or oxygen. Okay, so same family, similar chemical properties. We prefer you to go up and down, not side to side. Okay, they're grouped that way. Okay, so there's a lot of information that we can tell from an electron configuration. Okay, well, everybody, that wraps up electron configurations and everything that we want you to know from that. Okay, so have a great day.